In silence, the universe unpiles, a dome of blackness pricked by stars, each one a burning ember of the past. Their light does not belong to the present moment, but to ancient ages already gone. When photons fall into the human eye, they carry with them the memory of where they were born, traces of supernova, the glow of galaxies rising, the fading whispers of stars that no longer exist. The cosmos is not simply a landscape, it is an archive. Every flicker is a story told across time. To gaze upward is not to see now, is to see then. Every point of light is delayed, every vision an echo. The sky is not a mirror of the present, but a museum of vanished epochs. Imagine then a machine no longer of myth, no longer bound to imagination, but of steel, glass, and mathematics constructed not merely to dream of the past, but to seize it. A machine that stretches human vision beyond the limits of the eye, beyond the reach of earthly atmosphere, to catch the first glimmers of cosmic dawn. The Hubble Space Telescope once revealed galaxies layered like fossil strata deep into time. The James Webb Space Telescope now carries sight further still, peeling back the curtains of dust to uncover the universe as it was when it was young. These are not telescopes in the ordinary sense. They are instruments of time travel, machines that gather ancient photons and render them into stories. Yet their reach is not infinite. Beyond a certain veil, the cosmic microwave background light itself cannot carry memory. Here begins the paradox. Humanity builds machines that see the past, yet at the edge of time, a wall rises. The question echoes, can any machine look beyond the first light, into the darkness before creation itself? From the first time human eyes gazed into the canopy of night, there was an intuition and unspoken recognition that the sky was not simply decoration, but memory. The glimmering of distant stars was more than illumination. It was a message, carried across immeasurable distances, arriving late, delayed by the speed of light. Ancient peoples did not have the mathematics to prove this truth, but they sensed it instinctively. The night was a record, a time-stained tablet inscribed in fire. Stonehenge, with its massive stones aligned to solstices, was more than a monument of ritual. It was an early machine primitive, yet profound, designed to synchronize human life with celestial rhythm. In Babylon, clay tablets recorded planetary motions, their scribes noting with patient care the cycles of Venus, the eclipses of the moon. The Maya carved calendars that interwove cosmic recurrence with earthly destiny. These cultures understood in fragments that the heavens bore memory, even if they could not yet speak of it in terms of photons, waves, and relativity. Then, in 1609, Galileo Galilei lifted a crude telescope of Dutch design toward the moon. Through lenses not much more sophisticated than a pair of spectacles, he shattered a world of assumption. The moon was not a flawless, divine sphere, but scarred, mountainous, alive with valleys and craters. Around Jupiter, he saw moons circling a planet, tiny worlds that proved Earth was not the center of all things. The telescope became a true machine that revealed the past not because it bent time itself, but because it extended human sight into realms where light had carried stories from long before. Isaac Newton deepened this revolution. With his experiments on optics, he proved that light was not supernatural but physical, a spectrum that could be dissected, refracted, and measured. With his laws of motion and gravity, he turned the universe into a calculable clockwork. Yet, hidden in his equations was an implication that light traveled not infinitely fast, but with a finite speed. Centuries later, this truth would crystallize. In 1676, Al-Raqma made the revelation precise. Observing the eclipses of Jupiter's moon Io, he noticed irregularities. The timing of eclipses shifted depending on Earth's position in its orbit. He concluded that light had a finite velocity, about 220,000 kilometers per second by his estimate, close to the modern value of 299,792 kilometers per second. The conclusion was extraordinary. To look at the sky was to see history. Every glance upward was a glimpse backward in time. William Herschel, with his great reflecting telescopes in the 18th century, mapped the heavens and catalogued nebulae. He speculated that many were distant galaxies, though the term had not yet been forged. For the first time, humanity understood that starlight was not merely decoration, but the trace of other epochs, other eras, perhaps other universes of suns. With Herschel, telescopes became archives, not just instruments. The 20th century would deliver the decisive blow to the idea of a static cosmos. Edwin Hubble, working at Mount Wilson Observatory in the 1920s, used Cepheid variable stars as standard candles to measure distances. He discovered that galaxies lay far beyond the Milky Way, immense islands of stars scattered across unimaginable expanses. Were so more wondrous, he found that these galaxies were receding. The universe itself was expanding. Each telescope was not only a machine that looked outward, but a device that carried sight backward into epochs when galaxies were closer, younger, fresher in their formation. Then came a discovery that changed cosmology forever. In 1965, Arno Penzias and Robert Wilson detected a faint, persistent hiss on their radio antenna at Bell Labs. They tried to remove it, even cleaning away pigeon droppings, convinced it was interference. Yet the signal remained. What they had stumbled upon was nothing less than the fossil radiation of the Big Bang itself, the cosmic microwave background. This afterglow, older than stars and galaxies, was the earliest image the universe could ever yield to sight. Released when the cosmos was only 380,000 years old, before which it was opaque plasma. Humanity had found the first true boundary of vision. Every generation since has sharpened this vision. The Hubble Space Telescope, launched in 1990, gazed into patches of sky so small they appeared empty, only to reveal thousands of galaxies shimmering like a cosmic mosaic. The Hubble Deep Field showed us the universe as it was billions of years ago, when galaxies were still infants. Machines of steel and glass became time machines, each mirror and lens an extension of memory itself. In the decades that followed, Kobe, WMAP, and Planck mapped the microwave background with increasing precision, decoding its faint temperature fluctuations. These were not random, but fingerprints of the infant cosmos, primordial ripples that would seed galaxies, clusters, and the entire scaffolding of structure. By the dawn of the 21st century, it was clear telescopes were not mere instruments. They were machines that translated the past into present, carrying the human mind back across 13.8 billion years, from the stone alignments of ancient civilizations to the superconducting detectors of Planck. One thread remained constant: the recognition that to look outward is to look backward, and that the night sky is not a canvas of stars, but an archive of time itself. And yet, every extension of sight revealed a deeper limit. For beyond the cosmic microwave background, photons cannot carry memory. Beyond that veil, a greater darkness waits. The machine that sees the past had reached its first horizon, and in that horizon lay both triumph and mystery, the knowledge. That vision has a boundary. and that what lies beyond may forever remain untouchable. The revelations of the 20th century were not only dazzling but unsettling. Telescopes had proven themselves not just extensions of human sight, but instruments of temporal dislocation machines that allowed the past to pour into the present. Yet with this triumph came a sobering realization. The universe we see is never the universe as it is. It is the universe as it was. Every image of a galaxy, every star twinkling above the horizon, is delayed by the finite speed of light. The nearest star beyond the Sun, Proxima Centauri, appears to us not as it exists now, but as it was over 4 years ago. The Andromeda Galaxy, looming like a spiral ghost across the void, shines with photons that departed more than 2 million years in the past, when humanity itself did not yet exist. The Hubble Deep Field shows galaxies so distant that their light began its journey billions of years before Earth had cooled from fire into stone. The paradox is inescapable. Astronomy is history, not immediacy. To look outward is to look backward. This truth deepened with the rise of relativistic cosmology. The Big Bang model, reinforced by the discovery of the cosmic microwave background, implied that the universe had a definite age 13.8 billion years. Beyond that age, there was no starlight, no galaxies, no photons free to travel. The CMB itself, discovered by Penzias and Wilson in 1965 and later mapped by satellites, was both a window and a wall. It allowed humanity to glimpse the universe in its infancy, yet it also marked a hard limit. Before those first 380,000 years, the cosmos was opaque, impenetrable to light. This was the first profound shock that the universe itself imposed an observational horizon, not a limit of technology, but a limit of physics. No machine, no matter how advanced, could retrieve photons from before that epoch. The past had a veil, and sight could not pierce it. The second shock came with Hubble's expanding universe. Galaxies were not merely distant, they were fleeing, receding at speeds proportional to their distance. Beyond a certain scale, this meant galaxies moved faster than light could bridge. They slipped beyond a cosmic horizon, never again to be observed. Einstein's relativity permitted this space itself could expand without violating the speed of light, but the implication was devastating. The universe was actively erasing its own history, pulling galaxies out of reach as if drawing curtains across its stage. The Hubble Space Telescope brought this into sharper focus. In the mid-1990s, astronomers turned toward what seemed an empty region of sky no larger than a grain of sand held at arm's length. After 10 days of exposure, the darkness erupted into thousands of galaxies, each distinct, each ancient, each a beacon from billions of years in the past. The Hubble Deep Field was hailed as one of the most important images in human history, a portrait not of the present universe, but of its deep history. Yet embedded in its wonder was unease. All those galaxies had already evolved, collided, or faded. We could see them as infants, but never as they are now. Then came the most staggering shock of all. In 1998, 2 teams, the Supernova Cosmology Project and the High C Supernova Search Team, observed distant supernova as standard candles to measure cosmic expansion. They expected to find the universe slowing under the pull of gravity. Instead, they found acceleration. The universe was not decelerating. It was racing outward ever faster, driven by a mysterious force, later named dark energy. The implication was terrifying. The cosmic horizon was not fixed, but shrinking. With every billion years, more galaxies would disappear from view, crossing a boundary beyond which no photon would ever reach us. A universe once filled with billions of galaxies would, to distant future observers, appear empty, stripped of history, stripped even of its origins. The cosmos was not only veiled at its beginning, it was veiling itself in its end. Stephen Hawking extended this analogy through the concept of cosmic horizons. Just as a black hole swallows light at its event horizon, the universe itself imposed a boundary. There existed a cosmic event horizon beyond which events could never be observed, no matter how long one waited. The very structure of space-time erected a wall around knowledge. Beyond that wall, reality might continue, but it would remain forever invisible. Here was the deepest shock. Science, which had once promised total comprehension, now confronted absolute limits. Telescopes had revealed that light carried memory, but they had also shown that memory had edges, boundaries beyond which no recollection could exist. The machine that sees the past could reach far, but not infinitely. It was confined by the rules of physics themselves, and with this came a final, chilling recognition. Humanity lives in a privileged cosmic era. Today, we can see the microwave background, galaxies still gleaming, the traces of cosmic dawn. But in trillions of years, as dark energy drives everything apart, no such vision will be possible. Future astronomers, born in distant epochs, will look upward and see only darkness. The memory of the cosmos will be gone. The shock, then, is not only scientific, but existential. The machine that sees the past is also a reminder of impermanence. It reveals that knowledge itself has a deadline. It tells us that the universe is not an open book, but a manuscript with missing pages, some erased at the beginning, others destined to fade at the end. In that realization lies awe and fear and a haunting question. What does it mean to seek truth in a universe that hides so much of itself? The shock of cosmic horizons did not end exploration. Instead, it fueled a deeper determination. If the universe imposed boundaries, then science would approach those boundaries with greater precision, constructing ever more sophisticated machines to press against the veil. Each new generation of instruments became not only sharper eyes, but more intricate time machines, designed to recover subtler memories written into the cosmos. The first great leap was the Cosmic Background Explorer, COBE, launched in 1989. Before its flight, the cosmic microwave background was known only as a faint, nearly uniform radio hiss. COBE transformed that faint whisper into a map. It revealed tiny variations in temperature across the sky anisotropies, only 1 part in 100,000. These fluctuations were the fossil seeds of galaxies, ripples in the infant universe stretched across billions of light years. For this discovery, John Mather and George Smoot were awarded the Nobel Prize. The machine had seen not just the past, but the scaffolding upon which all structure was built. COBE's successor, the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, sharpened this cosmic memory further. It measured the CMB with unprecedented accuracy, confirming the age of the universe at 13.8 billion years and establishing the strange recipe of reality. Only 5% ordinary matter, 25% dark matter, and 70% dark energy. WMAP did not simply measure. It transformed cosmology into precision science. Each ripple in its maps became a data point linking the present universe to its earliest state. But even WMAP would be surpassed. The Planck satellite, launched in 2009 by the European Space Agency, delivered the most detailed portrait of the cosmic background to date. It traced temperature variations with exquisite precision, mapping the geometry of the universe and refining the parameters of cosmology. Planck revealed a cosmos that was flat to within a fraction of a percent, consistent with inflationary theory, and yet it also uncovered anomalies patterns that seemed to resist explanation. A mysterious alignment, nicknamed the axis of evil, suggested that the universe's largest scales might hold imprints of processes unaccounted for in standard models. The machine had pressed against the veil, and the veil had pushed back with mystery. Beyond photons, scientists sought other messengers of the past. Baryon, acoustic oscillations, frozen sound waves in the distribution of galaxies, became another fossil record. These patterns, observed through vast galaxy surveys, mirrored the ripples seen in the CMB, confirming the link between the infant universe and cosmic structure. They served as a ruler stretched across billions of light years, measuring how the universe expanded over time. With them, astronomers traced the accelerating hand of dark energy across history. Yet photons and galaxies were only part of the archive. To pierce deeper, physicists turned to neutrinos, particles so elusive they slip through planets as if through empty space. The IceCube Neutrino Observatory, embedded in Antarctic ice, and Japan's Super Kamiokande detector became instruments to glimpse the past, not with light, but with ghostly particles. The dream was to one day detect relic neutrinos, left over from the first second of the universe, even older than the microwave background. Such a detection would push the observational frontier back from 380,000 years to mere seconds after the Big Bang. Then came a revolution in listening to the past rather than seeing it. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime from the collision of two black holes more than 1 billion light-years away. Gravitational waves had been predicted by Einstein a century earlier, but now they were real. Virgo in Europe joined the listening, and soon neutron star mergers were recorded. For the first time, the cosmos revealed its history not only in light, but in vibrations of spacetime itself. Future detectors, such as the space-based LISA or pulsar timing arrays already underway, may capture gravitational waves from the first fractions of a second after the Big Bang, carrying information no photon could. Infrared astronomy opened another frontier. Where visible light was blocked by dust, infrared machines could penetrate. Spitzer and Herschel prepared the way, but the James Webb Space Telescope became the true masterpiece. Launched in 2021, it unfolded its golden mirrors 1 million miles from Earth, designed to see the first galaxies igniting in the darkness after the cosmic dark ages. Within months, Webb delivered images of galaxies more massive, more luminous, and more numerous in the first few 100 million years than theory had expected. The machine that sees the past had not only confirmed history, but challenged it, raising questions about whether our models of star formation and galactic growth were incomplete. The layering of these machines tells a story of human persistence. From Galileo's crude glass tube to mirrors the size of houses and detectors chilled to near absolute zero, each advance sharpened the focus, deepened the past, and revealed subtler patterns. But with each advance, a truth became clearer. No matter how powerful the machine, there would always remain a final silence. Supercomputers became partners in this pursuit, running simulations of universes under different conditions, testing which pasts matched the one revealed by telescopes. They recreated galaxies from quantum fluctuations, turning mathematics into artificial memory. Yet even here, models strained against the edges of knowledge. Simulations demanded assumptions, and assumptions could not pierce beyond the veil of the microwave background. The deeper the machines looked, the more they uncovered layers of structure: cosmic dawn, reionization, galaxy clusters, dark matter, webs. But the more the horizon loomed, the past was not infinite. Beyond photons, beyond neutrinos, beyond gravitational waves, there would remain a silence, untouched by any messenger. And so the investigation became not only scientific, but philosophical. Were these machines recovering the universe as it truly was, or constructing narratives from partial data? Were the anomalies glimpses of a deeper order, or artifacts of measurement? Was the past itself fixed, or was it, as some interpretations of quantum mechanics suggest, still emergent history as a story not yet fully written until observed? The machine that sees the past had grown vast, with satellites orbiting Earth, detectors buried in ice, antennas spanning continents, and mirrors unfolding in space. Yet every revelation carried with it the whisper of finality. The memory of the cosmos was astonishingly rich, but it was also finite. There would always be an edge, a boundary, a silence into which no instrument could reach. This recognition did not diminish the triumph. It made it more urgent, more poignant. Humanity, in this brief cosmic moment, had managed to build tools that could retrieve memories from billions of years ago, to watch the infant universe breathe its first light. And yet, each new discovery was also a reminder. The deeper one looks into the archive of the cosmos, the more clearly the limits of that archive appear. Here lies the paradox of deeper investigation. Each machine extends vision further into time, but each also sharpens the outline of the horizon. The past can be seen, but never completely. The memory of the universe is vast, but not infinite. The story continues, but always against the silhouette of a veil that will not lift. As the machines refined their gaze, what they uncovered was not a serene, orderly history, but a cosmos riddled with strangeness. The further science pressed into the past, the more the universe resisted explanation, as though each veil lifted revealed not clarity, but deeper enigmas. The machine that sees the past was supposed to recover a straightforward memory. Instead, it exposed contradictions, anomalies, and paradoxes that unsettled even the most confident. Frameworks of cosmology. One of the first deep shocks was found in the data of the cosmic microwave background. When the Planck satellite released its exquisite maps, cosmologists expected only statistical noise decorating the otherwise uniform glow. Yet the maps displayed curious alignments on the largest scales, subtle patterns that refused to be dismissed. The so-called axis of evil seemed to indicate that vast regions of the universe shared orientations in ways no theory could justify. The CMB, once hailed as the cleanest memory of the early cosmos, began whispering of secrets we might not understand. Some suggested unknown foreground contamination. Others dared to hint at processes from beyond the observable universe, fingerprints of pre-cosmic physics. The James Webb Space Telescope added its own layer of unease. In its first months, Webb revealed galaxies that appeared more massive, more luminous, and more numerous in the earliest epochs than standard cosmological models had predicted. According to established theory, galaxies should have taken hundreds of millions of years to grow into such structures, yet Webb showed them already mature in the dawn of time. Was the machinery of star and galaxy formation more efficient than imagined? Or had cosmology itself miscalculated the rhythm of the early universe? The machine that sees the past had, in a sense, caught the universe acting out of script. Beneath these discoveries lies the larger riddle of inflation, introduced to solve puzzles about the uniformity and flatness of the universe. Inflation posits that space itself underwent an exponential expansion in a fraction of a second after the Big Bang. It stretched quantum ripples into cosmic patterns, leaving the subtle anisotropies observed in the CMB. But inflation, elegant as it is, spawns new mysteries. Its equations suggest that inflation might never completely end. Instead, while it halts locally to form universes like ours, it continues elsewhere, spawning endless bubbles in an eternal multiverse. If true, then the machine that sees the past can never retrieve the whole story, for most of creation lies forever beyond reach. The memory we observe is only of our cosmic bubble, one page in an infinite library. Compounding the mystery is the discovery of the cosmic event horizon, the accelerated expansion of the universe, driven by dark energy, ensures that galaxies beyond roughly 16 billion light-years are receding faster than light itself. These galaxies are not only invisible today, they are gone forever from our sight. No future machine, no matter how powerful, will ever retrieve their light. The universe is actively erasing its own memory, pushing its history beyond observation. With each passing epoch, the deeper we see the past, the more we realize how quickly it is slipping away. This realization carries a haunting temporal paradox. Humanity lives in a uniquely privileged era. We are born into a cosmos still young, enough that the CMB remains visible, galaxies still populate the sky, and the structures of cosmic evolution can still be mapped. Trillions of years from now, the microwave background will fade into wavelengths too long to detect, and galaxies will vanish beyond the event horizon. Future astronomers, even with machines far beyond ours, will look into a sky of silence, unaware that a Big Bang ever occurred. The universe is not only hiding its beginning, it is actively erasing the evidence of its origin. Even within the evidence we still possess, puzzles multiply. The CMB anomalies, the early galaxies, and the distribution of matter on the largest scales all whisper of tensions with standard cosmology. Measurements of the Hubble constant are present. Expansion rate of the universe differ, depending on whether they are inferred from early universe data or late-time observations of supernova. This Hubble tension might indicate new physics at work, perhaps an exotic interaction of dark energy or flaws in the very models that underpin cosmology. The machine that sees the past is catching conflicting memories, as though the universe is telling two different stories of itself. Beyond cosmological puzzles, the nature of the past itself becomes unstable. Quantum mechanics suggests that at the smallest scales, reality is governed not by certainty but by probability. What, then, is the status of the early universe we believe we are observing? Are we seeing a fixed history, or are we reconstructing a probability field collapsed into narrative by the act of observation? Some physicists speculate that the anomalies we see may be artifacts of the quantum nature of reality, hints that the past is not a single line but a spectrum of possibilities. All of this escalates the stakes of cosmology, the machine that sees. The past has succeeded in reaching further than imagination once dared. It has shown galaxies only a few 100 million years after creation, mapped ripples from the first moments, and listened to space-time itself. But with every triumph comes a sharper mystery. If galaxies formed earlier than theory allows, then what drives their growth? If inflation is real, then what lies beyond our horizon? If the CMB carries alignments unexplained, then what unknown physics lurks behind them? The questions do not end with history. They extend into philosophy. If the universe is actively erasing its memory, what does that mean for the permanence of knowledge? If the multiverse is real, is our observable past even meaningful in a larger context? And if the past is quantum in nature, are we ever seeing the universe as it was, or only as it chooses to reveal itself under our observation? The mystery deepens, not because machines fail, but because they succeed. Their revelations force us to confront paradoxes embedded in the cosmos itself. The machine that sees the past is not betrayed by its limitations. Rather, it faithfully transmits a universe whose story is stranger than any narrative we expected. And so, escalation arrives not in silence, but in a crescendo of contradiction. The more the past is revealed, the more fragile our understanding becomes. The archive of the cosmos is vast, but it is also unstable. The horizon does not merely block us, it taunts us with hints of truths just out of reach. What began as a triumph of observation has become a confrontation with the possibility that the ultimate past, the true beginning, may forever remain hidden in this way. The machine that sees the past is both revelation and torment. It shows us what no eye could ever otherwise see, and in doing so, it sharpens the awareness that beyond its vision lies a realm we will never know. The mystery is not diminishing, it is deepening, accelerating, expanding with the cosmos itself. The revelations of the machine have brought us to a precipice. What it sees is dazzling, but what it implies is unsettling. The cosmic past, once expected to be a simple story of expansion and cooling, has instead unfolded into a theater of enigmas. And so theory stretches, straining to encompass the weight of the data, searching for frameworks vast enough to hold the universe's contradictions. These speculations are not idle. Each is an attempt to reconcile the fragments of history retrieved by our machines with the deeper architecture of reality itself. At the heart of speculation stands inflation, a theory that has become both cornerstone and riddle, proposed to explain why the universe appears so smooth and uniform on large scales. Inflation imagines that in the first trillionth of a second, space itself expanded faster than light. Quantum fluctuations, tiny jitters in the vacuum, were stretched into cosmic ripples, later to become galaxies and clusters. Inflation explains much of what the machine has seen: the near-uniform glow of the cosmic microwave background, the distribution of galaxies across billions of light-years. Yet inflation is not a single theory, but a family of models, and some predict strange consequences. Eternal inflation suggests that, while our local bubble stopped inflating elsewhere, it continues endlessly, birthing infinite universes in an eternal multiverse. If this is true, the past our machines reconstruct is only one local chapter in a story with no end and no single beginning. Other frameworks propose even deeper revisions. Roger Penrose's conformal cyclic cosmology imagines that what we call the Big Bang was not the beginning, but a transition. In this vision, universes follow one another in endless cycles, each expanding until its material contents dilute into radiation, which through mathematical rescaling becomes indistinguishable from the smooth state of a new Big Bang. If true, then the machine that sees the past might detect traces of previous eon subtle circles in the cosmic microwave background, overlapping imprints from black holes long evaporated in an earlier universe. Loop quantum cosmology offers yet another speculation. Where relativity predicts a singularity, quantum geometry may dissolve it into a bounce. The Big Bang might not have been creation from nothing, but a rebound from a prior collapsing cosmos. If so, the machine that sees the past is not viewing a beginning, but a turning point in an eternal oscillation. In principle, signatures of such a bounce could linger in the fine structure of primordial fluctuations, whispers encoded in the oldest light. String theory, that vast mathematical framework, where particles emerge as tiny vibrating strings, adds its own possibilities. Extra dimensions compactified beyond sight may have influenced the very earliest epochs. Collisions of higher dimensional brains could themselves have sparked big, bang-like events. If our cosmos was born from such a collision, then the machine is peering into the aftermath of a higher dimensional drama. Evidence, if any exists, might be found in subtle departures from perfect randomness in the microwave background, or in the distribution of gravitational waves across the sky. Speculation also touches on the fate of the universe and its connection to the past. Dark energy, the mysterious driver of cosmic acceleration, may not be constant. If it evolves, then the history we reconstruct may be only a fragment of a larger, changing dynamic. Some models imagine quintessence fields slowly shifting across cosmic time, altering the rate of expansion in ways that could leave fingerprints in the growth of structure. More extreme ideas invoke phantom energy, a force that could rip the universe apart in a big rip, disassembling galaxies, stars, atoms, even space-time itself. In such a scenario, the machine that sees the past is not just looking backward, it is glimpsing the fragility of the present. Quantum physics contributes further strangeness. The notion of vacuum instability suggests that the Higgs field, the quantum field giving particles their mass, might not be perfectly stable. If so, the universe exists in a false vacuum, a metastable state that could one day tunnel into a lower energy configuration, destroying everything in an expanding bubble at nearly the speed of light. Though speculative, the machine that sees the past could, in principle, detect imprints of early universe physics tied to this instability, slight anomalies in the primordial fluctuations that betray the nature of vacuum itself. And then there is the holographic principle, born from the study of black holes. According to this idea, the universe's three-dimensional reality may be emergent, encoded on a distant two-dimensional surface. If so, the past our machines recover is not stored in vast volumes of space, but written on a cosmic boundary like a film projected into the theater of existence. To peer into the past would then be to decode an informational tapestry, suggesting that time itself may be less fundamental than the information that underlies it. Some theories blur the line between physics and philosophy. What if the past is not fixed but emergent? In quantum mechanics, observation collapses probabilities into definite outcomes. Could it be that the deep past is not a static memory but a reconstruction shaped by present observation? If so, then the machine that sees the past is not revealing a pre-written history but co-creating it, weaving memory from probabilities into narrative. This radical view suggests that history itself is participatory, that the act of seeing reshapes what is seen. These speculations may never all be confirmed, but they serve a deeper role. They remind humanity that the past is not simple, not static, and not easily captured. Each new machine expands the archive of cosmic memory. Yet with every revelation, the architecture of theory must bend to accommodate new contradictions. The past, far from being a settled ledger, is dynamic, a shifting frontier where mathematics, observation, and imagination intertwine. The machine that sees the past does not merely return images. It provokes questions. Why are there galaxies too early, alignments too strange, accelerations too abrupt? Why does the CMB glow with patterns that hint at processes beyond? Is our universe one bubble among countless others, or the latest cycle in an eternal rhythm? Each speculation, from inflation to the holographic principle, is an attempt to make sense of what the machine shows. But perhaps the deeper truth is that the machine has revealed something more profound, that the past is not a stable object to be retrieved, but a mystery that deepens the closer it is approached. In the end, speculation is not indulgence, but necessity. For without it, the machine's revelations remain fragments, isolated images without story. Theories, whether inflation, cyclic, cosmologies, string landscapes, or quantum holography, the narratives we weave around those fragments, tentative architectures of meaning. And though many will be discarded, their role is vital. For in the darkness, beyond the last photon, beyond the last observable galaxy, lies not silence, but possibility. And it is into that possibility that speculation reaches, daring to imagine the unseen chapters of the universe's origin. The pursuit of the past is not guided by memory alone, but by machines forged to reach beyond the limits of the human eye. Each generation of instruments is both an extension of the senses and a wager against the silence of the cosmos. If the universe is indeed an archive, then these machines are its librarians' tools, designed to collect, decode, and preserve the faint traces of what came before. Their evolution is not merely technical. It is philosophical, for each embodies the question of how far humanity is willing to go in order to know. The James Webb Space Telescope stands as the most ambitious of these devices. Suspended 1,000,000 miles from Earth, its mirrors unfurled, like a golden flower in darkness, with its infrared eyes cooled to near absolute zero. Webb is capable of capturing the first galaxies, shining faintly just a few 100 million years after the Big Bang. Unlike Hubble, which revealed the richness of galaxies across time, Webb aims to reach the epoch of reionization, the moment when the first stars ignited and burned away the cosmic fog. In its observations, astronomers hope to confront one of the central paradoxes: why galaxies appear more massive and luminous earlier than theory predicts. Webb is not only seeing deeper, it is testing the scaffolding of cosmology itself. But Webb is not alone. On Earth, the rise of colossal observatories promises complementary visions. The extremely large telescope in Chile, with its mirror spanning 39 meters, will resolve structures in the distant universe with unprecedented sharpness. Its siblings, the giant Magellan Telescope and the 30-meter telescope, each strive to glimpse the earliest galaxies, measure the faint absorption lines in their spectra, and probe the chemistry of the first generations of stars. These megatelescopes will not peer as far back in time as Webb, but they will dissect what Webb finds, transforming faint smudges into detailed histories. Beyond light, new machines extend vision into other messengers. The Square-Kilometer Array, the most ambitious radio observatory ever conceived, will map hydrogen across cosmic history. Neutral hydrogen, the most abundant element, carries the memory of the universe's cosmic dawn. By mapping its faint signals, SCAR may reveal how galaxies assembled and how the first stars transformed their environment. It will trace the timeline of reionization with exquisite detail. writing in radio waves the chronicle of the young cosmos. Other instruments attempt to probe epochs hidden even from light. The cosmic microwave background has been mapped by COBE, WMAP, and Planck. But the next generation CMBs, FOR and Lightburdens, to search for the faint curl patterns in its polarization, a potential signature of primordial gravitational waves. If found, these patterns would be evidence of inflation, a fingerprint of physics at energies far beyond the reach of any particle accelerator. These missions represent humanity's last attempt to mine the photon background for deeper secrets. If successful, they will open a direct window to the first instance of cosmic expansion. Gravitational waves, once theoretical, are now a confirmed messenger. LIGO and Virgo have detected the collisions of black holes and neutron stars, events that ripple spacetime itself. But future observatories, like LISA, the Laser Interferometer, Space Antenna, promise to extend this listening to the early universe. Suspended in space, 3 spacecraft forming a triangle millions of kilometers wide will detect lower frequency waves, potentially capturing echoes from the cosmic dawn or even from inflation itself. If photons fail to reveal what happened before the cosmic microwave background, gravitational waves may succeed, for they pass unhindered through the opaque plasma of the infant cosmos. Neutrinos, the ghostly particles that barely interact with matter, form yet another channel of history. Today, detectors like IceCube and Super Cameo Conde capture them as faint flashes of light in deep ice or underground water. But future neutrino observatories aim to detect relic neutrinos, left over from the first second after the Big Bang. These particles, if found, would extend the machine that sees the past into epochs far earlier than photons can reach, unlocking a chapter of the universe's origin, otherwise forever sealed. Even the world of the very small becomes a window into the very old. Particle accelerators, like the Large Hadron Collider, probe energies that mimic conditions of the early universe, testing how fundamental fields behaved in its first microseconds. Though no collider can reach the energies of inflation, they may reveal instabilities in the Higgs field, symmetries of nature broken in the first moments, or hidden particles that shaped the cosmos's evolution. Future colliders, larger, more powerful, are envisioned not merely as experiments in particle physics, but as laboratories of cosmic archaeology. In parallel, quantum simulations create analogues of the cosmos in miniature. Bose-Einstein condensates, cooled to near absolute zero, can mimic event horizons, producing radiation akin to Hawking's predictions. Other experiments attempt to simulate the emergence of spacetime itself, hinting that time and geometry may not be fundamental but emergent. From quantum entanglement, these laboratories are not telescopes in the conventional sense, yet they extend the machine inward, probing the conditions where theory fails. And behind all these instruments lie the supercomputers, silent engines of mathematics that simulate entire universes. With billions of particles and trillions of interactions, they reconstruct cosmic evolution from first principles, testing whether observed structures match predictions. They are not passive observers, but active creators of virtual cosmoses, comparing the machine's view of the past with possible histories that theory allows. Each of these tools approaches the past from a different angle, yet all confront the same boundary. Photons reveal only to 380,000 years after the Big Bang. Neutrinos may extend this vision to seconds after. Gravitational waves might reach back to inflation itself. Particle physics explores the fields and symmetries that governed those moments. Together, they form a chorus, each voice carrying fragments of memory across epochs, but they also reveal the fragility of knowledge. As dark energy accelerates cosmic expansion, more galaxies slip beyond the horizon, never to be seen again. The farther future will erase the cosmic microwave background, leaving only silence. This makes the present unique. The machines of our time are not merely tools, but guardians of memory. They exist in the brief window when the universe still speaks its story. The machine that sees the past, then, is not one instrument, but many, scattered across Earth and space, tuned to light, sound, neutrinos, and gravity. Together they compose a network, a collective organ of perception. They are humanity's answer to the silence of the void. Each a declaration that no distance is too vast, no epoch too ancient, no veil too opaque. Yet for all their reach, they will never break the final horizon. The past they recover is deep, but not infinite. And so, in laboratories and observatories, in deserts and orbits, science continues to build. Each tool pushes the horizon a little further back, each one sharper, colder, larger, more daring. Together, they form the last generation of machines before darkness claims the rest. Their mission is not only to see, but to preserve the memory of a universe that is already erasing itself. For the cosmos will not wait. Galaxies recede, photons thin, signals fade. The machine must listen now, while there is still a story to hear. The cosmos, when seen through glass and mirror, through detectors and simulations, reveals itself not as a present, but as a memory. Every star, every galaxy, every flicker of radiation is a relic of a world that no longer exists. To look outward is to gaze backward, and to build telescopes is to construct bridges, not to distant places, but to vanished times. Humanity has crafted machines that see the past, yet in doing so, it confronts the deeper paradox. The universe grants vision not of what is, but of what has been. This paradox is as humbling as it is profound. For millennia, human beings imagined themselves at the center of creation. Now, standing on a small planet orbiting an ordinary star, they realize they are witnesses not to the living universe, but to its ghosts. The galaxies observed in the Webb's golden mirrors, brilliant and immense, may no longer burn. The light that dazzles now is the light of the dead. The machine that sees the past shows not eternity, but transience, a cosmos where even galaxies vanish in time. And yet, within this fragility lies wonder. For though the stars die, their light endures across billions of years, carrying their memory to worlds that never knew them. The act of observation transforms photons into history, silence into story. In this sense, astronomy is less the science of stars than the art of memory. Each measurement, each image, is a fragment of the universe remembering itself. But there is a horizon. The cosmic microwave background, faint and omnipresent, is both the oldest light and the final veil. Beyond it lies a silence into which no photon carries news. No telescope, no detector of light will ever see beyond that wall. Even gravitational waves and neutrinos, though they promise glimpses further back, will reach limits of their own. Beyond those limits, there is only speculation. Beyond them lies the dark. This horizon raises a question more philosophical than scientific. What does it mean to live in a universe that is only partly visible, partly knowable? Does reality exist only where equations and instruments can reach? Or is there a truth beyond the veil, inaccessible to sight, but no less real? If so, then perhaps science, for all its triumphs, is not a conquest, but a pilgrimage, a journey not to total knowledge, but to the edge of knowledge itself. And there is time to consider as well. The present is unique, a cosmic moment where the past remains visible. Billions of years hence, the sky will empty. Dark energy drives galaxies away. The microwave background fades. The fossil record of the Big Bang will dissolve into noise. Future civilizations, if they exist, will not know the cosmos we see. They will inherit silence, a sky stripped of history. For them, the machine that sees the past will find nothing. The memory of the universe will have been erased. This too reframes meaning. Humanity exists in a privileged epoch, not merely capable of building telescopes, but capable of building them while the sky still speaks. The past is not a constant archive. It is a fleeting gift, already fading. The duty of these machines is not only discovery, but preservation. Every spectrum, every map, every simulation becomes an act of defiance against cosmic forgetting. And yet, even preservation confronts limits. A record is not the thing itself. A photograph is not the galaxy it portrays. The real past remains, beyond reach, beyond retrieval. In this sense, the machine that sees the past is also a mirror, showing humanity its longing not only to know, but to remember. The drive to look back is the same drive that shapes myths, histories, and civilizations. The refusal to let time erase meaning here. Philosophy and physics converge. If the universe is finite in what it shows, then perhaps meaning does not lie in answers, but in the act of asking. The cosmos does not promise transparency, it promises mystery. Each machine built, each image taken, is not an end, but a continuation. The horizon does not close the story it writes, the next chapter in silence, waiting for imagination to follow where photons cannot. The question remains, is the past a fixed record, or is it shaped by observation itself? Quantum mechanics suggests that reality is not independent of measurement. If this is so, then every act of seeing may not merely retrieve history, but participate in it, weaving present and past into a single fabric. Perhaps the light that arrives at Webb's mirrors is not a passive message, but part of a dialogue between cosmos and consciousness, between the infinite and the finite. What, then, does this mean for humanity? Perhaps that its greatest machines are not only technical triumphs, but spiritual ones. They reveal that to know is not to possess, but to glimpse. That to see the past is to accept that it is gone. That to confront the horizon is to recognize the limits of the human condition. In this way, astronomy does not diminish humanity's place in the cosmos, it deepens it. For though small, fragile, and transient, humanity dares to build machines that see across billions of years, into times when Earth itself was not yet formed. And so the final meditation emerges. The machine that sees the past is not only Hubble, or Webb, Planck, or LIGO. It is not only mirrors, detectors, or supercomputers. It is the human mind itself, the imagination that turns faint light into meaning, that reads silence as story, that refuses to accept the horizon as an end. These machines are the outward expression of an inward desire, the ancient longing to know where we came from and what it means that we are here at all. The last vision is simple yet infinite. A universe fading into silence, galaxies receding, horizons closing, but within that silence remains a flame, the flame of curiosity, fragile but unyielding. As long as it endures, so too does the machine, not of metal or glass, but of thought. The eternal observatory is not in orbit or on mountain tops, is in the act of wonder itself. The past, then, is never fully gone, for though light fades and records end, the questions endure. And in those questions, humanity finds not only knowledge, but meaning.